Hello students, welcome to the course Verilog HDL. In the previous 5 to 6 videos, we gone through the gate level modeling with the different primitive gate types and also gate delays. Okay. So to understand this concept better, so we'll solve some of the exercises. So total 5 questions are there. So in this video, we'll try to solve 2 questions and remaining we'll see in the next video. Okay. So note on the first question. Create your own two input Verilog gates called my OR, my and my NOT from two input NAND gates. Check the functionality of these gates with a stimulus module. Okay. So previously what you have done, so you have used the Verilog primitives for OR and NOT. Don't know how they are constructed. Okay. But now there is an exercise. You need to construct your own my OR, my and my NOT from two input NAND gates only. Okay. So this is something you have learnt in basic electronics in digital electronics module, right? In the module 3 maybe. So constructing a basic gates from NAND gates only. Okay. So that is the question here. So for this you need to do the design now. Okay. So to write here logic symbol, truth table and much is not there because it is primitive gates only. So you can start your design from gate level picture. Okay, so how you have the construct my not from NAND gate. Okay, my and from NAND gate, my or from NAND gates. Okay, so from there you can begin and you can check the output. Okay, so first not gate, just I will show you not gate how you construct from NAND gate. So NAND gate is two input, right? So NAND gate is a two input NAND gate, but not gate is a single input. Okay, so I am just recalling, I am not going to explain you much here. So what you used to do for not gate, just you are shorting the inputs, right? So I call this as A and I call this as C1 output. Okay, so C1 is equal to A bar. Okay, so it is A dot A bar actually. So two inputs are A only. A dot A from Boolean algebra is A itself, that's why it is A bar. Okay, so this is how you construct your own my not from NAND gate. So you have to call the NAND primitive and you have to give the output as C1. Okay, some variable. So output this one and then A is the input. Okay, so this is third gate. Now I will call it as C3. Okay, so first NOT gate is required. So I will call C1, C2, C3 as the outputs. Okay, so third one I am writing first because NOT gate is required first to understand, right? Then AND gate you have to construct. What is AND gate? Output A dot B, right? So what is NAND gate output? So second gate I am doing. Okay, so I'm writing from mouse. My writing may not be clear, so hope you understand. Okay, so these are the two inputs A B. Okay, so this is A dot B bar, right? So this is A dot B bar, but the output should be in the form A dot B. So for that what you have to do, you have to do one more complement. So how to bring this? Just use a NOT gate in. Okay, so NOT gate using NAND gate. Okay, so just shorting the output, so you'll get the final output. So I call this as C2 here, second gate, so which is equal to A dot B double bar. Okay, which is equal to A dot B. Okay, so from the algebra you know A double bar is A itself, right? So now in the design I will call this as some variable E. Okay, because I need to store this, right? So I have to call first NAND gate. E is the output, A B are the inputs. Then I am calling NAND gates, so E is the input, two times I am calling, and output is C2. Clear? Similarly we have to construct OR gate. So OR gate, so what is the OR gate expression actually? A plus B, right? So but to bring it NAND gate form, you should have a dot and you should have a complement above that. Okay, so like this. Okay, it should be in this form. Dot should be there and complement should be there. To bring it, we will use the De Morgan's theorem. So for example, I call this as C1. Okay, so C1 equal to A plus B. I will complement both sides, so it will become C1 bar, so which is equal to A plus B bar. Okay, so whatever C1, C2, C3 I have used here, it is used in the program itself. Okay, that's why no need to confuse. That's why I've used the same notation. Okay, so when you do De Morgan's theorem, so what is the output you will get? A bar dot B bar, right? So this complement is splitted among individual complements, right? So now dot you got, but above that whole complement is not there. So that's why we will do one more complement both sides. So C1 bar, one more bar, which is equivalent to C1 itself. And here you will get A bar dot B bar whole bar. Okay, so now this only we will implement using NAND gates. To get A bar B bar, how to do? You require two NOT gates. Okay, so this you have done already, so just I am recalling. A and similarly B. Okay, A B you got, that means what? This is A bar and this is B bar. So now these two you have to AND it, right? So if you just use one more NAND gate here of output of this, so what is this output? Nothing but I called C1, which is in the form now A bar dot B bar. These are the two inputs there, right? And this bubble is there here, whole complement. So which is from the expression equal to A plus B. Hope it is clear. So to represent these in gate, so I will call this as A1 variable, because A bar B bar you could not write it in program, right? That's why I will use A1 B1 I will use. Okay, so first NAND gate output is A1, A 2 times I'm writing as input. Next second one B1 output, BB I'm writing 2 times input, and final gate NAND gate I'm calling C1 as the output, A1 B1 as the input. Okay, so this is your my not, my and my or gate. So this is what you have to do first. Okay, so this you have learnt already in the basic electronics, so that's why this question is asked. So now the whatever gate level diagram is there, we will write the corresponding Verilog description now. Okay, so just you have noted down. Okay, otherwise you pause the video and note down. Okay, so we'll see the program. So this is the program here. So module, I have written all the three in single program. So called it as name my gates. So C1, C2, C3 are the outputs, right? C1 is my or, C2 is a my and, C3 is not gate, my not gate. Okay, and A and B are the inputs. So that's what written here, declaration of ports, input and output. Then wire we have used. Okay, so for OR gate I have used A1 B1, right? So wire I have used. So this first part is about OR gate. So two NAND gates are called, as I told you, A1 comma AA. Okay, so this will implement the A bar. Then second NAND gate B1 is the output, BB called twice. Okay, so this is B bar. So then one more NAND gate is called, that I named as my OR. Okay, so C1 is the output, and output of this NAND gate. Okay, that is A bar and B bar are the inputs. Okay, so your my OR gate is constructed. Similarly, my AND gate, you had one more variable there, E declared here. Then NAND E is the output there, and AB we have given. Okay, so that is now in the form A dot B bar, single bar is there. To bring it in normal form, so one more NAND gate is called with a NOT gate, right? My and E called twice. Okay, so now it will give A dot B double bar, which is equal to A dot B. Okay, and output is stored in C2. That is the my AND gate. My NOT gate, very simple. So NAND you have called my NOT. C3 is the output, A called twice. Okay, so this is the my NOT gate. Okay, so here declaration is written in between, so no issues with this. Okay, even you can write the both declarations first and then you can write the design anyhow. Okay, anyhow within the module and end module you can write this, no issues. Okay, if you are not written, and then it will raise an error, somewhere you should write it. Okay, so it is to make it, it is belongs to AND gate, belongs to OR gate. Accordingly program is written. Okay, hope this program is clear to you. Okay, so now we have to test this design using values for a and b. I have to give 0 0 0 1 1 0 1 1. For that I have to write a stimulus module. Okay, so we'll just write the stimulus module, so you know what is stimulus module is having. So initially module name, it does not have any list of ports or port declarations. Okay, so module stimulus, then inputs are declared as register, outputs are wire. Okay, so earlier programs we used to have write the instantiation first, then monitor statement or display, and then we pass the inputs, right? Here I have written the inputs first, then instantiation, then monitor. So no issues with this. Okay, so you have to write any order, but it should be within the module and end module of the stimulus module. Okay, so that's why just to show you this way also you can write it. So I have taken this example. Okay, so begin, initially we are giving the values of AB, which is 0 0. Then we have at the time simulation time I'm changing 0 1. Next 1 0 I am making, then 1 1 I am making, right? So this is the first block. Okay, initial. So it is begin and end. Then my gates, your design I have called, that is with name. So user defined module, no, that's why you have to call the instance name compulsorily. Same way pass the outputs and inputs in the same order. So variables have used in the same, okay, in the both the design, because this is variable declaration is local to this module, that's why no issues. Okay, then we are writing the monitor statement, because as soon as AB value changes, so corresponding C1 C2 C3 output will change. So to note that monitor we have written once. Okay, so dollar time, it will compute the time 0, second time 10, next time 10 plus 10 20, next 20 plus 10 30, that it will display in this. Then AB whatever value you are changing, it will be shown here, and the outputs will be next shown. Okay, C1 C2 C3, and the this initial statement and the module. Okay, so a stimulus module should have declaration of variables, passing of inputs a b or whatever inputs you have, then calling the gates, this is important. So without that computation will not happen. Then whatever you have given, so just you have to display it on screen. Okay, so for that this is the module. Okay, all these are compulsory here. Okay, so as we write more exercises, you will clear with the stimulus writing also. Okay, we'll see the output now. So 0 0, how the display output will happen. So this is how. Okay, so at 0 time, so a is 0, b is 0, right? Initially a b 0. So first C1 is OR gate, so 0 plus 0 is 0, and gate 0 dot 0 is 0, a is 0, that's why C3 is 1, a complement 1. Next 10 is the simulation time, so we have changed the input 0 0 to now 0 1. So here you will get the value 1 now because of addition 0 plus 1. Here multiplication will be 0 0 dot 1 and gate, whereas a is still 0, that's why output C3 is 1. Okay, not gate. Then 10 plus 10 20, simulation time is now 20 at 20 time minutes. So value of AB changes to 1 0 now, and C1 is 1, same because 1 plus 0 is there now, so it is 1. C2 still it is 0 because 1 dot 0 is 0, and C3 now changes to 0. So there is a new value because A changes to 1, complement of 1 is 0. Then next 30. Okay, so 30 you have, so A equal to 1 and B equal to 1 will happen in the AB inputs. So C1 is 1 only because 1 plus 1 is 1 itself, no changes. C2 now changes to 1 because both are ones, and gate both inputs are 1, then output is high. C3 is 0 as in the previous case because A is still 1. Okay, so this is the verification output. Okay, even this you can write it in single line. Okay, so in my text it is there like this, I have copied. Okay, so you can write it in single line. Okay, A B C1 C2 C3 like that. Hope so with this exercise you understood how to write the design. Any design is given, first you need to write the gate level description and gate level diagram, then from that gate level description, and from that you will write the stimulus module and verify the output. Okay, so with this knowledge, so now we will do the second exercise which is close related to this. Okay, so just note down the question. A two input XOR gate can be built from my and my or and my not gates. Okay. Construct an XOR module. Okay. In Verilog that realizes logic function z equal to xy bar and x bar y. Inputs are xy and z is the output. Write a stimulus module that exercises all four combinations of x and y inputs. Clear? So this you have to do. So they already given the logic expression, so no need to write the logic symbol and truth table. So why we write truth logic symbol truth table? If they have told some design without any boolean function, okay, already they have given the boolean function, that means third stage they have given. So from boolean function we can write the gate level diagram now. So straight away we can go with, so how to write the this one. So here to build the y bar and x bar you require the not gates, right? So that's why we'll use my not instead of calling the Verilog primitive gate. So we'll just call this my not program, whatever we have written using not gates only, that only it will be instantiated now. Okay. And then y bar to implement not gate, then two products are there here, x dot y bar and x bar dot y. So to implement these two products you require the mine and gate. Okay. And then in one plus is there, so you have to add these products. So for that or gate is used. Okay. So with this knowledge, so how you construct your gate, sorry. So first x and y bar. Okay. So this is x, so x, and then y will be complemented with your own my not gate. Okay. I will show this same, this one, this is your my not gate. So both these are ANDed, right? So AND gate is used, and that output is x dot y bar. Okay. Then similarly x bar y you have to implement, so x not gate you have to connect. So here y bar is there. Okay. And here now x bar will come. Okay. Output of this, and then y will be as it is given. So this AND gate, it will construct now x dot y bar, sorry, x bar dot y. Remove this. Then you have to OR it both the products. You have to use a OR gate. This is your own my OR gate. Instead of Verilog primitive you have to call that, and this is the output z. So if you write the logic symbol for this, okay, so what it looks outside, x and y are the inputs, okay, and z is the output in the module. Okay. Your own my XOR gate you are writing now, my XOR. So xy is the input, z is the output. Inside that how it is constructed. So here one variable is required, here one variable is required for holding the not gate output, and here two variables are required holding this product values. Okay. And accordingly we'll map that to gates. Okay. So just we'll write the name as my or, my and, my not. Okay. That's it. So these variable names we'll see in the figure what we have used, so that only you write it in this diagram. Hope clear. So we'll write the Verilog description now. So module my XOR. Okay. So you have constructed your own XOR gate now. Z is the output, XY is the input. Okay. So that is what done is list of ports and port declarations. So this is what the name we have given. Okay. So nothing to confuse. So X output, X bar is given X underscore N, because X dot hyphen N we could not write. Okay. X bar also we could not write. So X underscore N, Y underscore N for Y bar. Okay. Then X underscore NY is written. That means X Y bar, and XY underscore N for X bar Y. Okay. So here some mistake is happened. Okay. XY underscore N. Okay. Y underscore N, here X underscore N it is. Okay. So this is X bar Y here, and this is XY bar. So same notation. Okay. It is done. Okay. So these are the four variables used, okay, in our program. So first I'm implementing the not gates. Okay. My gates. So from my gates, now I am using here connection by name, right? So connecting by name I have used, because in the my gates only I have the three gates, right? So that's why my gates I have called M1, M2, So dot C3. So C3 is the output there implementing the NOT gate. So dot C3 x underscore n is the output. Okay, their output is C3 and here our output is x underscore n. Okay, and here our output is input is x. There it was a in our my NOT gate. Okay, so similarly second NOT gate y underscore n is the output here. There it was C3 and here it is y output. So a was the input there. Okay, so hope this is clear. Only with variables we have given, maybe you feel difficult. If you are comfortable with any other variable, you can use that. Okay, so just to show you how to write with ordered name. Okay, so connecting ports by name, so this we have used it. Okay, because it may confuse, right, the ordered list. Okay, you could not remember, that's why this is best method. Okay, in this case, next we have to implement the two products, not of x bar y and xy bar. Okay, so for that again my gates is called with instance name now m3 and m4. So first output. Okay, so what was the AND gate output then? C2, and here it was x underscore ny. Okay, that is x bar y it is implementing first. For x bar y, what is the input? X underscore n. Okay, the this NOT gate output, right? So x bar n, okay, and y. So that gate it is a b and c2 was there. Okay, so I don't repeat it again and again. Next AND gate, what is the xy bar? Okay, so xy bar is the output, x and y in the complement form, so that's why this is used. Okay, then finally how to use a OR gate to add those. So my gates m5 is called. So c1 was the output there in the design, so here it is z. And what is the inputs? The output of the AND gate, whatever you have here first line, this you can write here, x bar underscore ny, xy underscore n. Okay, so ab is the input, same, it will not change. Here it will change, c1 c2 c3. So two NOT gates, two AND gates, and one OR gate is required to construct your own my XOR gate. Okay, so even if they have asked the XOR gate, so straight away you would have used the primitives, but they have told you to do it using your own my AND, my OR, and my NOT gates. Hope this design is clear. So you can pause the video and you can just verify. Okay, is there any problem? And then you can continue. Okay, so now we write the stimulus module for this same way. Now x and y will give the inputs 0 0 0 1 1 0 1 1, same. So stimulus module won't change. Only thing is I have changed the x and y here. Instead of a b and c1 c2 c3 I have z now. Only that is the change. Remaining all it will be same. So see the stimulus module, you can compare. Okay, so no such different things. Module stimulus, instead of ab I have written input as xy declared as register, and output is only one here, z declared as yr. Next I have written the initial block for passing the inputs. So first case it is written 0 0, then I have given 0 1. So for that you have to see the last bit here. This is the value actually, 0 1 and then 1 0 and then 1 1. So all the four combinations of x and y are given. Next you have to call your design. Your design is now my XOR gate with instance name x1. So pass the inputs and outputs z x y. Next you have to monitor statement. You have to write whatever you have passed, what output it is giving. So dollar time to calculate the time, then xy values whatever you are giving it should be done. And what is the output? XOR gate, what is the output you will get? 0 0 0 0 1 1 1 0 1 1 1 0. So that output you have to see. Clear? So hope this is simple gates. Okay, so with that only we have started the programming. So just if we see the simulation output now, so 0th simulation time. Okay, so you have the x and y inputs 0 0, so output is 0. Okay, then at simulation 10 10 0 plus 10, so input is changed to 0 1, so z is changed to 1 now. Okay, even you can pass these values with each individual gates, not gate. Okay, how it will change the value you can observe. Okay, then x equal to 1, y equal to 0 1 0, it is changed. So simulation time 10 plus 10 20 now, so z is also 1. Okay, then 20 plus 10 30, so x and y values are changed to 1 1 now, both are 1, so z value changes to 0. So this is the output of an or truth table of an XOR gate. Okay, so to verify your output you require the truth table. Okay, so since this is a basic gate, you remember. Okay, this anyhow throughout the engineering, or after you finish engineering you go to some other field also, you will not forget these truth tables, right? Such a things, right? Hope. Okay, so with this you understood. Okay, so tomorrow we'll see, in the next video we'll see the remaining 3 questions. Okay, so with this I will stop here. Okay, go through this again. Okay, so stimulus module, design module, and how and we are doing. If you have any doubts, make note as the classes begin, so you can clarify that. Okay, thank you.